Hi there. Yeah, so quick caveat, this is actually my PhD work that was done at the University of Leeds. So excuse the yellow shellified backgrounds, but University of Leeds work. So today I'll be discussing the depositional styles of the Mungaroo Formation using a combination of seismic and well logs. Okay, so during the talk I'll give a quick introduction to the study area and go over my data set. I'll have a quick whip through my seismic interpretation methods that were frequency decomposition and stratal slicing. I'll then try and apply those techniques to interpret the depositional styles of the Mungaroo Formation using 4 different intervals of the Mungaroo Formation, and finish off with a quick summary of the depositional model. So my study location was an exploration block on the Exmouth Plateau, and that forms part of the Northern Carnarvon Basin, so that's the bright yellow one. And at the time of deposition of the Mungaroo Formation, the northwest shelf of Australia was sitting on the southern margin of Tethys. And the deltas of the Mungaroo Formation formed from a continental scale drainage system that covered the whole of Australia. Okay, so my data set comprised a 3D seismic survey and 12 wells. The location map on the top left shows the location of the wells within the seismic survey, and 3 of those wells had core. The shaded box, I should just say, within the survey extent is what is the area I used for my more focused spec decomp study. Okay, I interpreted 12 seismic horizons within the survey, and the bottom 7 of those are within the Mungaroo Formation. So, the top figure shows a west to east correlation panel with an overview of the regional well picks, and within the well logs it was possible to identify 3rd and 4th order surfaces, and these fitted within the framework of the seismic units that were identified. And the key well picks that we used were mostly flooding and transgressive surfaces, and they were correlated to seismic events. So the bottom right-hand figure just attempts to demonstrate why I used flooding surfaces instead of sequence boundaries. And apart from the fact that sequence boundaries are pretty difficult to interpret sometimes when you're working in fluvial systems, you tend to have a problem where they're based at the bottom of your valley deposits, which enters into a whole other discussion of whether or not you're really looking at valleys or just big channels. The other problem is that obviously the channel sands are quite laterally discontinuous. They don't turn up in all your wells, and even if you do have them sitting next to each other, they're not always related to the same stratigraphic interval. And on the seismic, as you can see, no big surprises, very laterally discontinuous sand bodies, but you can pick out some mud surfaces that are your flooding and transgressive surfaces. Still not easy, but a lot easier to interpret. So in order to better image my deposits, data conditioning was carried out, and this briefly comprised using a median filter and some stratally aligned filtering, fairly basic stuff, just try and knock out some of the noise. My dataset was especially noisy because I was using the near stack volume, so it basically on the far stack volume, a lot less noise, but a lot of the smaller channel bodies just weren't visible. So I then used spectral enhancement, and this was used to boost some of the higher frequencies. Again, unfortunately, boosting the noise, but it does help bring out some of your thinner deposits. But what you go for is a really kind of wormy-looking, messy, original volume, and some areas where you think there might be some incised deposits, to something that's a lot smoother. And trust me, after 4 years of looking at it, honestly, it is quite a lot easier to see the incised deposits on the smoothed-out volume, but maybe you just have to take my word for it. So, because the whole area had been affected by post-depositional faulting and tilting, if we just looked at time slices, you couldn't see any of the fluvial deposits. And one way to get around this is by making flattened volumes. And essentially it turns your seismic time slices into horizon slices, which show you some of the deposits that are stratally aligned with the horizons. Depending on what package you're using or what company you're in, you might be calling it proportional slicing, sculpting, or goodness knows what else. So, if you look at the top right figure, that's one of my horizon slices, and it shows what appears to be a distributary network of channels. So on to spectral decomposition. So in some of the intervals, because I was working with quite deep deposits. We've got fairly poor seismic imaging, and in those cases sometimes spectral decomposition did help out. So just in case anyone isn't familiar, you create 3 different frequency volumes which hopefully show contrasting deposits, and when they're blended together you get a bit of a better contrast between what are interpreted as the kind of channelized deposits and the overbank deposits. Okay, so for the rest of this talk I'm going to discuss 4 different intervals of the Mungaroo Formation using the seismic and well techniques I've outlined. So the first interval that I'm looking at is my deepest, and it's between the first and second seismic horizon. And the wireline logs show thicker than, up to 50 metre thickness sandstone bodies. And when we looked at the core data, these were interpreted as high energy channel deposits, that's the red. And when we looked at the dip log data, that they were interpreted as mainly downstream migrating bar forms. And so there really wasn't any overbank deposits preserved at this interval, and so it kind of led us towards an interpretation of possible incised valley deposits. If we look at the reflectivity slice, as I said, it's very deep. There's not much contrast between what might be valley deposits and what are non-channel deposits, but you can see the outline of some of the larger deposits, but not really any of the internal architecture that might be there. If we look at the spectral decomposition slice, you can see there's a bit of a better contrast between what are the kind of valley deposits and the kind of interluvial non-channel deposits. And if we focus on the area in the white box, you've got a fairly crisp outlined possible valley deposit, and within it these kind of bright yellow deposits. And they were interpreted as moderately sinuous channel belt deposits within an incised valley. And these deposits could actually be traced out over a 40 millisecond window. And when you stack them on top of each other, you can see the subtle lateral migration of the channel belt deposits within the valley. So hopefully you can see quite a good uplift in the quality of interpretations you can make. And if we were going to look for a modern analogue here, you'd be looking for incised valley, fairly moderately sinuous channel belts, but downstream accreting bar forms. And these photos just show a couple of examples of possible analogous systems in Madagascar. Okay. So the second interval that I looked at was between the second and third seismic horizon. And it's got a lot more of a variable wireline log. We've got some fairly thick sand packages, but also a lot of overbank fines. And when we looked at the core, we had high energy channel belts and low energy channel deposits. We also had some glacial deposits indicating a very poorly drained floodplain. We also had some crevasse splay deposits in the kind of green and yellow, and the pink deposits represent interdistributary bayfill, and the biostrat did seem to indicate some periodic marine influence. And oh, there we go, that's one of my more splay-dominated sequences. And if we look at the dip logs using a little bit of creative license, it seems like we have lower sinuosity high energy channels and higher sinuosity kind of low energy channels, and also some splay channel complexes. If we look at the reflectivity slice, actually this interval is pretty well imaged, and you can, hopefully all of you can pick out the nice big channel belts and what look like kind of messy areas of splay belts over the side, and the bright areas indicating more kind of mud-rich overbank deposits. So this shows the area that I used for spectral decomposition. It's just a rough map interpreting the kind of channel belts, splay belts, some of the minor channels, and organic rich mires. If we look at the spectral decomposition slice, actually, it really didn't help that much. It was pretty messy, and at this interval, a lot of channels that can be seen are actually ghosting down from the interval above. But still, if we focus on one of the areas that was previously interpreted just as amalgamated splay belt, that's just kind of here, we managed to interpret a couple of abandoned channel loops in there. So not much extra information, but it still can give you a little bit. So if you were expecting just to find some splay belts with laterally continuous, very thin sands, you might be in for a bit of a nasty surprise with some muddy abandoned channels in there. And so for a modern analogue, we'd be looking for channel belts with splay belts alongside of them and some minor channels as well. We'd be looking for a fairly poorly drained floodplain and hopefully some deltaic influence. And I just use the Athabasca River as an illustration of that, where we've got this kind of lower sinuosity main channel, splay belt running alongside, and a much more high sinuosity channel as well. Okay, so the third interval I used was just beneath the 6th seismic horizon, and it wasn't cored. But the wireline logs show, show some thick intervals of sandy deposits and quite a lot of overbank fines and muddy packages. And if we look at the reflectivity slice, so this is actually taken from one of my previous studies where I tried to link seismic facies to the lithology. And it worked quite well in this interval because there was quite a lot of, again, it was a lot of organic rich, widely spread areas that contrasted quite well with the sandier channels. And yeah, so what you've got is quite a lot of large channel belts, smaller channels as well, and the kind of blue areas are muddy, coaly mire areas. So the reflectivity slice within the focused area seems to show this fairly kind of broad feature that was originally interpreted as either a large amalgamated channel or possibly even kind of one of these big, large multi-valley deposits because it's quite thick as well. But and so then if you try and sketch out where you think the sand might be, one of the wells that was drilled looks like it should be kind of quite nice and sandy at this interval, sitting in the middle of this nice wide deposit. But when we look at the spectral decomposition, it's not that simple. What we've got are a lot of channel belts. Some of them are going, as you'd expect from the southwest up to the northeast, but a lot of them are kind of kinking out over towards the west and southwest. So what we've really got more of is just kind of autogenic clustering and some nodal avulsion going on of channel belts. And the rusty coloured areas kind of show where the sand-rich deposits are, but these kind of blue and green areas are channel margin and overbank deposits. And that's where you realise we might be running into a bit of a problem because the well's actually sitting right on the edge of one of the interpreted channel belts. And sure enough, if we look at the wireline log at that interval, it missed the main channel and hit the channel margin silty deposits instead. So again, if you rely solely just looking on your reflectivity data, you might be missing some detail. And if we look for a modern analogue, no real surprises. We're looking for a fluvially dominated delta with a very poorly drained delta floodplain, lots of distributive patterned channel belts, and lots of floodplain lakes. So I looked at the Kobuk River. And the final interval that I looked at is from my uppermost interval in the Mungaroo Formation. And the wireline logs show some kind of either silty sands or some stacked heterolithics. And these were from the core interpreted as tidally influenced interdistributary bayfill, and these were overlying some IHS belts, and they were interpreted as tidally influenced point bar deposits. If we look at the reflectivity slice, we really don't see much. Kind of got some vague outlines of some of the larger deposits, but again, not much information on the internal architecture. But the spectral decomposition slice really does show quite a difference. You've got quite a lot of contrast between what we've interpreted as channel belt deposits and the overbank fines. And there's also some hints of lateral accretion going on in there. And the image to the right just shows out a quick sketch map of one of the more easily interpreted deposits. And for a modern analogue, I looked at the Peace River just to give a bit more of an idea of what might be going on beyond the resolution of the seismic, showing overprinting of channels, point and counterpoint bar deposits. So in order to keep with the time, I'll just briefly mention that I looked at a range of autogenic and allogenic controls that could be used to explain both the overall stacking pattern of the Mungaroo Formation and also try to explain what the architecture and arrangement of the channel belts at each of the intervals I studied could be. I used Holbrook's buffers and buttresses model to describe the Mungaroo Formation as a series of stacked fluvial buffer zones controlled by an overall base level rise, but punctuated by brief relative base level falls. And the deposits of the Mungaroo Formation broadly fit within an evolving fluvially dominated delta system. Okay, so yeah, if anyone has any questions, happy to take them now.
Thanks very much, Dan. Are there any questions?
Yeah, it's an interesting study and some good results. Thank you. I wondered if you could comment on the commercial implications of the work, for future exploration.
Yeah, I imagine that by now spectral decomposition will be new to pretty much no one in the room, but it's just that sometimes it can be seen as an extra thing that takes a lot of time, and do we really have time, and is it really worth the effort? And as you can see, if you plan your wells based only looking at your reflectivity data, you could think that you're sinking a well into the middle of a lovely big valley deposit and get a nasty surprise when it turns out what you've actually got is a series of stacked smaller channel belt deposits. If you planned it correctly, you could get a whole bunch of them stacked together. If you plan it wrong, you're going to go straight through a bunch of siltstones, and these were pretty deep wells. They cost a lot of money, and you really don't want to miss your reservoir. So that's about it.
Any more questions from the floor? Right, thank you very much.